Again, I'm Waqas.
I'm JJ Plank.
You've probably seen him many times before. More of a fresh face around here. But today we're going to be looking at the Michelson interferometer. And to be specific, we're looking at PASCO's precision interferometer. And what we're doing here is we're taking a look at the wavelength of laser. We have a helium HENE laser, helium neon laser here. And what we're going to do is, we want to look at the wavelength of the laser.
We're trying to experimentally determine the wavelength of the light source.
So what an interferometer is it's a device that lets us look at one light source. It lets us create two wavelengths so that we can compare the two wavelengths in order to figure out what's going on.
Two beams of light from the same source, right? And they have their own wavelength. And the whole idea is, can we get them out of phase? And if they're out of phase, then we're going to see interference, basically.
Thanks, Vin. So the way the interferometer works is we're shining a laser straight through here. There's a beam splitter here. There's a mirror here, and an adjustable mirror back here.
And then in the manual, you'll notice sometimes this will be called the fixed mirror, even though it's adjustable.
And actually, we're able to adjust both of these mirrors, but we'll go over that. So the light enters through here, it hits the beam splitter. The light splits off into two paths. It gets bounced back off of both mirrors, and then it goes through the beam splitter again, and then we can see the projection or the result on this screen here. And what we're doing is, because the light gets split up into two, we now have two different light beams.
Two different paths.
Two different light paths. And we can use this micrometer adjustment here. We can actually adjust this mirror back and forth and change the phase of the second path of light.
Yeah, right. They hit the beam splitter, and the same coherent beam gets split into two. And then those two beams take two different paths. And then we bring them back together. And if the paths are the exact same length, we won't notice any difference, right? They'll be in phase still. But if we change the path of one of them, we make it slightly longer or slightly shorter, now there's a chance that the phases, those two beams might be out of phase when they come back together, which is exactly what we see.
Cool. So the way we have this set up here, we're actually projecting the output, I'm going to call it, onto this tiny screen here. But the cool thing about this is that, in your classroom, you don't want, 130 students are huddled up in the front. You can actually project onto like a board that's behind you. The further back the board is, the bigger the image is. And we're actually going to use a little bit of a trick here. We'll show you that we can also try it with the lens as well. This may not show up as nicely on camera.
Yes. So like when the lights are on in your classroom, this is perfect. You can shine it up on the whiteboard. Kids can see it from a short distance, but sometimes, the students from the back of the classroom might be having a hard time. So there's this lens that we could use. And it comes with the set.
Use the optional lens. We have our bright lights on here, but it really just blows up the image. And in order for you,
yeah. Well, here, leave it on there for a second, and then we shut the lights off. Now you can see the
fringe pattern. Yeah,
the fringe pattern is a lot bigger. So now students in the back of the classroom can see it, and you can see in the pattern there's bright spots and then dark spots. Right, these are fringes, right, where we're experiencing constructive and destructive interference, basically. So those two light beams come back together, and if they're in phase, you get constructive interference, and if they're out of phase, you get destructive interference. And whether or not that happens depends on how much further or how much shorter one of the beams has traveled compared to the other one when they come back together.
So one thing that I'm going to switch back to the smaller. So one thing you'll see here is, as JJ mentioned, the dark spots are actually where they're out of phase.
That's right.
So that means that the beams are canceling each other out. So students might wonder, well, how can how do I know that that there's actually like this, there's light hitting this whole entire circle, but because there's two different phases, we're seeing the dark spots. If I just cover one of the paths, you'll see it's a full laser beam. Or if I go ahead and cover the other path, it's, as solid as you can get with the laser.
Your hand's covering them. Yeah, so you can't see that interference pattern unless you've got both of those beams coming back together in the same place, and one of them has to be out of phase with the other one. Otherwise, it would just be back to its original, beam self when it entered the system.
So the way we get the wavelength here is we want to adjust the micrometer here, which actually, as we mentioned earlier, I might want the light on for this.
Yeah, maybe we can turn this back on.
So we're going to adjust the micrometer. That's going to change the distance. That's going to adjust this mirror here in microns based off the units here.
Yeah, so the beam comes in, it gets split, and it goes this way, and then back out, and then it goes this way, and then back out. And so adjusting the micrometer moves this mirror back and forth, which makes this other path shorter or longer, depending on how we move it. Basically.
So every, like 1 micrometer that we adjust this, the light beam actually gets adjusted twice as much because of both directions. So it gets adjusted in the direction going to the mirror, and it gets adjusted in the direction coming back from the mirror.
Yeah, right. We shorten the path of the incoming beam, and we shorten the path of the outgoing beam as well.
So because of that, for every, so you'll see here, as I turn the micrometer, we'll see the fringe pattern here. It's like a Doppler type of effect.
Yeah, it's like evolving dark to light,
right.
and they're moving. The fringes are moving, right?
And every, micrometer that I'm adjusting this, it's actually adjusting half a wavelength because we're adjusting this mirror. It's out of phase. We have equations for it, but it's adjusting basically half a wavelength.
Yeah, so you'll see here in the bullseye, the table's a little shaky, but it looks bright right now. But if you adjust that micrometer enough to move this mirror 1/2 of a wavelength, you're going to see a full wavelength of shift in phase between those two beams, and it'll cycle from that bright to dark back to bright again. So we'll go through a full wavelength shift, moving this 1/2 of a wavelength, basically.
So the best way to start data collection is to, so you'll notice we don't really need a computer for this. We don't need an interface or anything. Everything's right here. We set the micrometer to a fixed position. So I have it, essentially zeroed out. I'm looking at the pattern here. I'm going to draw a line somewhere on this, and I'm going to adjust the micrometer and just count the number of times. I'm going to count, let's say 20 times that the pattern is going to go over the black line. So if I just go, let's see, it's 1, 2, 3, 4, 5.
Yeah, and you keep counting as they go by. You count them. And you want to do like 20 or more, right? So if you count it 20 times as it goes past that black line, like a dark fringe goes past that black line, right? That means we've cycled through that many wavelengths of phase between them. And then that distance, or the distance that this mirror's moved, then right, what the wavelength of the light should be to equal that amount of wavelength shifts.
All right, so I've gone over it 20 times. Here we moved around about 18.5 or so micrometers. And then again, we have an equation. We double that just because of the double the distance of, or we're looking at half a wavelength change. So, we essentially double this, we do some math, and we end up getting the wavelength of the laser beam, which is around 500 or so.
This one, I think, is probably about 632.
Okay.
Yeah, maybe 633. 632 point something. Generally, the lasers, this modulatable laser, I think, has it written on the back. It might be right here. Nope, that's just power.
Yes, 6 to 700. 6 to 700.
Yeah, but we can publish it. And you can also, if you have a laser and you know the wavelength, you can use that laser to calibrate this apparatus as well. So you can kind of do this in 2 ways: calibrate it and then use it to find the wavelength of an unknown laser, which would be, this would be a perfect example of the unknown laser wavelength.
So we kind of quickly explained over, the use of the interferometer. What's good about the precision interferometer is we actually have a variety of accessories available for it. And the one that we're going to be looking at first here is the main one we're going to be looking at is this vacuum cell. So I can place this here, and instead of adjusting the mirror to adjust the beam, what we can do is we can create a vacuum inside. Inside of this piece, there's 2 pieces of glass, and of course there's this vacuum hose. So I have a vacuum pump here, And I can, as I take the air out of it, it's going to adjust that pattern. So real quick, I'm going to go ahead and take the air out of the lens inside, and Jay's just going to hold it down for me.
Hand down. Hand down.
Let's see. There we go. All right.
Yeah, and so what Waqas is doing as he pumps the air out of this little vacuum chamber, right? He's effectively changing the index of refraction inside that chamber. And in doing so, you're going to change the number of wavelengths that fit in that chamber. So if this is full of air at the same pressure as the air around us, it's not going to experience any difference. But if you evacuate that chamber, the index of refraction is going to go down. It's going to get closer to vacuum, right? The speed of light in a vacuum. And in doing that, you're affecting the number of wavelengths that fit in here, which also affects the phase difference when they come together right here.
So there's two ways to do this experiment. One is to count the number of changes in the fringe pattern as you're taking air out of the system. What I find to be easier is to take the air out, and then as I slowly release it, then we're doing the same thing. We're just going to count the number of marks. So, you know, I have about in inches mercury, or looking at about 26 right now.
Mm-hmm.
And then I can just slowly release this, and we can like count 20 times over the marker. So about, whoa. You got to be very precise.
So yeah, you can do it by, you can do the same experiment by counting the fringes and measuring the pressure as you evacuate it, right? Or you can do it the opposite. As you let the air back in, there's a little relief valve on the pump that will let you let the air back in slowly. And so you'll count the number of fringes as they move by and the pressure, and then you can use those values to experimentally determine the index of refraction of the air, right? The atmospheric air.
So I just slowly adjust this. You'll start seeing the pattern change. Whoa. It was working out better when we were doing this earlier,
but yeah, so I mean, you can do it this way by pumping. So you can slow squeeze that pump and
there you go.
And observe changes in the fringe pattern while also measuring the difference in pressure as you evacuate it.
And I mean, there's other clever ways of doing this too. I mean, it's just going so fast that we can't count it. But you know, if you're using a cell phone, you can record the video and watch this change as the number of fringe patterns change. You can slowly, you know, sweep over that video with the cell phone, or you can of course do something like that in Capstone as well. If you want to use some more advanced tools. But yeah, as you can see, if I'm taking air out of the system, the pattern is collapsing in. If I release the vacuum, then it's going the opposite direction.
Yeah, and the math associated with the experiment, it's not necessarily very complicated. I mean, it's lengthy, don't get me wrong. But, you know, using algebra and some simple geometry about, you know, what's going on here, and your understanding of, you know, how wavelength and frequency are related at different speeds, you can figure out exactly what the phase difference is between those two waves as they come here, as they meet, or I should say here, meet here. And then you can use that to experimentally determine the index of refraction of whatever gas is in here. And now you can, so this cell here is designed for evacuation only, right? This is the one that comes with that accessory pack. You could use your own cell here, and you could pump your own gas into it if you wanted. And those gases, you know, at different pressures, or different gases, I should say, will have different indices of refraction. And so that's some more experimentation you could do. This interferometer is a tool that's used to determine the index of refraction of that gas that's in there. So that's another fun experiment. And you can also, this comes up out of here, and I can take this cell off. All right, mind you, the interference pattern is still there, and I can take a glass plate. And so the kit comes with this glass plate, and it mounts right to the front of this, as you see. And then we can put that back in there, and we can adjust, we can figure out, we can experimentally determine the index of refraction of that glass using the same kind of setup, except what we're doing in this experiment is, instead of changing the index of refraction through the medium, we're just going to change the angle, right? And so there's a little tilt arm, and as I tilt the arm, you'll see the fringe patterns evolve the exact same way. And in doing so, I'm changing ever so slightly the path length of the beam as it goes through there. And so it's effectively like moving this this movable mirror. Now again, the math is not overly complicated. This setup can get complicated, but it's definitely doable. It is lengthy, but in the manual you'll find the equations to help you determine those indices of refraction. They simplify quite well, and just with a couple small measurements and some counting of fringes as they move, you can figure out those unknown indices of refraction. And so, like again, if I move the angle here, you'll see the fringe pattern evolves. And then the last,
with the compensator.
Yeah, the last thing that I want to talk about is, so this light source is a beautiful coherent light source, right? This is a helium neon laser. We know that these types of lasers have a very coherent, the light that comes out of it is very coherent. If you're using a light source, and you can use other light sources, in fact, you could use a white light source if you wanted to, the experiment becomes, and setup and alignment becomes slightly more complicated, but you can help simplify that by adding this compensator. And so all this compensator is just it's a piece of glass that's identical to the beam splitter without silvering, without that partial silvering or partial mirroring on one side.
And the reason this matters is, so the light, as we mentioned, it travels in two paths. When it goes this way, it goes through, so this piece of glass here, the mirror, has a reflective side and a clear side, right? So the light has to travel through the reflective side, hit the mirror, and then bounce back, right? So that's 2 times it got distorted in the glass. Comes back to the mirror here, goes back forward, and again, it has to travel now through here. So that's 3 times the path got distorted. However, when we look at the light as it hits the mirror, it goes through once.
Yeah, just once.
Hits the mirror, comes back, and then it reflects on here. It only gets distorted 1 time. And by distorted, meaning it has to travel through the medium of the glass at some angle.
It's path length. So yeah, the path length as it goes through that beam splitter, it goes through glass, then hits the mirroring,
right,
and then goes back through the glass. And in those 2 transitions, there is a little bit of a path length difference compared to if that mirror wasn't there. And then again, it comes back through it 1 more time. And so the before it comes and meets up here at the screen, and the light beam that goes this way goes through this glass once,
right,
and then reflects off this surface, because the silvered or the mirrored side of this beam splitter is on the surface that's right here on this side.
So, because it has to travel through glass 3 times here and 1 time here, we're adding this compensator plate to, make the light go through 2 more essential stops, two more transitions of glass, so that it goes, 1, 2, 3, and then bounces off the mirror and comes back out.
Yeah, so those differences in path lengths, because of the refraction as it goes through there, we compensate for it by putting the compensator in there. And so with the laser, we didn't really need it because it's a very coherent source, but if we had like a spectral tube or let's say a monochromatic LED source or something like that, the compensator, you're gonna need the compensator. That way you can, produce these fringe patterns that you see here.
And have an even playing field, so that, we're looking at similar light.
Oh, there's one other thing that I wanted to do. Here, I'm gonna take the compensator out. So there are, in the manual, there's some great suggestions for additional experiments. And like I said, the Michelson interferometer is a great tool. Like, you can use this to measure unknowns. So you can learn about it, you can learn how it works, you can understand how these fringe patterns are created, and learn about waves. But then you can also use this tool to measure unknown indices of refraction, measure unknown wavelengths of light sources, those sorts of things. And also what's really neat is, let me see. So that interference pattern, when we had that vacuum cell up there, we changed the pressure of the gas that was in there. So we can also sort of demonstrate this, or we can demonstrate it by using a candle flame. In this case, it's just a barbecue lighter. And if you look at the fringe pattern, as I bring that flame near the beam, you'll see it distorts it. And you can actually see, in some cases, the edge of the flame as it goes through the path of one of those beams, right? And just like we changed the pressure here, let's see, we'll do it over here. And we can do it in either beam. You see it changes that fringe pattern, the way it looks there. because we're changing the temperature of the air, right? We're changing the pressure. We're changing the speed at which light travels through it, right? So we're changing the index of refraction just like we did with that vacuum cell there. So there's some really cool demonstrations you can do just with this amazing piece of equipment.
Yeah, that's a cool demo. Did want to highlight just some of the, if you do have this apparatus and you're having some trouble getting it right, there is some, you know, I'll run over the instructions on how to set this up. The easiest way to set, so now that we've shown you what the experiment looks like when you have this, you know, nice circle here, the best way to set this up is to do it one piece at a time. So by the way, we have this convex lens at here that helps us, you know, grow the beam, but we're going to take that off. The simplest way to set this up is to align the laser with the mirror here. You basically want the light to hit the mirror and go straight back.
Yeah, you want the beam to be parallel with the surface, the top of this.
Right.
Yeah.
So we want to make sure that mirror back here is number one, it's straight, and that the path is, you know, it's just boom, boom, straight back. Once we have that, then we can add our beam splitter here, and so might be hard to see on the screen, but as this beam splitter, see, these are the two light beams that get created. So I want to try to line those up as closely as I can. All right, I'm just gonna.
Oh, and you can kind of see it there. So there's reflections off of the mirrored or the reflecting surfaces, but there's also reflections off of the glass surfaces themselves. So you'll get these stray reflections, and you can kind of see them in there. How it's not a single beam there. There's actually 3 little dots next to each other. But the idea here is whatever those patterns look like, once you can get them right on top of each other, right? You know that those beams, as they travel their paths and come back together, they're going to land right on top of each other, and so we'll experience the phase differences or the path length differences will be as close as we can get them. And you can actually see it. Well, maybe not, but there are the bright spots. But then there's like a secondary fringe pattern in there. I can see it from interference off of some stray surface.
So, you know, as you see, like we've now got the beams right on top of each other. At least as close as we can do it. When I add the 18mm convex lens, you'll see what happens here. This is what makes it so that it's bigger, right? There you go. And also, like, if you're not seeing the bullseye pattern, you can adjust the mirror in the back, and
yeah, that fixed mirror, it's called fixed mirror sometimes, and also a movable mirror, or excuse me, adjustable mirror. It's because it has this XY, this gimbal adjustment in the back that you can use to make, fine tune where the pattern goes, basically.
And as I adjust that, I can use that to center the alignment of the two beams. And then...
Yeah, and you'll notice that the compensator's not in there, but if it was in there, right?
Yeah.
It doesn't really change what you see a whole lot. So you still see the fringe pattern, and it still moves as you adjust the micrometer, right? So now if this was a light source that wasn't quite so coherent, then this would almost be a necessity to make this setup work. Also, when you make measurements, right, Waqas explained, we're going to adjust the position of this mirror by turning that micrometer, the barrel on the micrometer, or the thimble, I guess, on the micrometer. When you make your measurements, here's a tip. Make sure you start by spinning that thimble a couple of times, or at least one full revolution before you begin your readings. That way you can eliminate backlash. So micrometers experience backlash when you change directions. And so you'll spin it one full revolution, and then you'll continue in that same direction to make your measurements, basically. And if you do go back, change direction, make sure you do one full revolution before you start those measurements.
All right. Yeah, are there any questions for...
I've been answering questions as they've come up.
Okay. Yeah, so we've been answering questions in the chat as they've been coming up.
Yeah.
So thank you, Brett, for taking care of that.
Oh, and this interferometer is set up right now in that Michelson configuration, right? Mm-hmm. Right. This is that famous luminiferous ether experiment that they did. a long time ago.
About 100 or so years.
Yeah, right. It was in the 1920s. So this system can also be used in a Fabry-Perot as well as a Twyman-Green setup. And so the manual outlines real well how that Twyman-Green setup can be used to find imperfections in optical components. I said this is a tool that can be used for not only explorations about light and wavelength, but also to help determine imperfections or inconsistencies in optical components. And then the Fabry-Perot setup does basically the same thing, except instead of the beam going down, being split and then going down and recombining as it goes to the screen here, it goes through a surface and then reflects in there, and those reflections escape. And the path length for each one of those reflections is different because one beam will go straight through, will not straight through. It'll experience some refraction.
Yeah, so you should be able to see the manual on the screen. And as JJ mentioned, the theory of operation, we have the Michelson, Twyman-Green, or the Fabry-Perot. We have like the 3 experiments we did today and suggestions for additional experiments, which I think that's where the lighter idea came from. I don't know, but that was pretty cool.
If you can get the path length to change, or I shouldn't say the path length, or the index of refraction to change, right? In either of those beams, you're going to see changes in the interference pattern because there's changes to the phase shift, the phase between those beams.
Yeah, I mean, we put this together for you pretty quickly today. So this is an experiment that it doesn't take a lot of time to set up. Pretty straightforward to use. PASCO does make it really easy for you. I don't know if you can still see the screen, but we try to include all of the accessories you'll need. The basic kit comes with a certain handful of accessories, and then if you buy the additional accessories package, then you get the vacuum pump and some of the other bonuses. So yeah, any other questions that have come in?
No?
It's just that awesome.
Yeah. All right, I guess that means we answered every question on this experiment that's possible today. So well, thank you very much for joining us today for this day of experiments.